Hello there, welcome back to the new video. So today in this video, we'll again do a research paper walkthrough where I'll be going through this paper from Carnegie Mellon University, which is titled as Pre-train, Prompt and Predict, a systematic survey of prompting methods in natural language processing. So since it's a survey paper, so as expected, it's going to be pretty long. So to tell you the numbers, it's roughly around 31 pages long, excluding the appendix section. So let's see how much can I cover in this 30-minute video. For whatever would be left, I'll make a follow-up video for that. Cool. With that said, let's start with the abstract. So this paper surveys and collates all the research work that has been developing this new paradigm of natural language processing, which we call as prompt-based learning. So if you can recall, under the supervised condition we are trying to train a model, the idea is to have a model M that will learn this probability function that if you give it an input sample X, it will try to get its output label Y. So this is how essentially a supervised learning problem works. So even if you talk about the fully supervised condition, so which is before this pre-train and fine-tune paradigm, where let's say you have a model M and let's consider a task of sentiment analysis. You would give it many sentences along with the actual label of whether that sentence is positive, negative or neutral, and then learn certain weights based on the back propagation for this model M. And then you freeze it out, and for any new inference you just pass a new sample and you already have the freezed weights. You use them to transform the input sample to get this label Y. And during the learning process, the idea is to minimize the loss so that you can maximize this probability. So yeah, that was about the fully supervised thing. Now when the shift happened and we moved to pre-trained and fine-tuned stage, the basic idea behind that was, why not train a model to first learn how language is written? And when the model has attained that level of proficiency, then we can tune it further for the downstream task. So then around 2016, 2017, we started seeing the emergence of pre-trained followed by a fine-tuned paradigm, where you would pick or maybe possibly train, if you have enough computation, a language model on large set of corpus. Now again, training a language model could have different objectives. So as we proceed forward in the paper, we'll see what all possible techniques are. For now, let's consider you have a language model trained, or let's say you have picked some open source model, and let's take that example to be BERT. Now to let's say fit BERT to do the sentiment classification, one of the basic ideas is to kind of use the head embeddings, add certain number of layers over there and do a classification. And now while doing the back propagation, these extra layers are going to learn weights that are too much specific to that particular task. Again, this depends from task to task. You might want to sometimes also tune the BERT parameters and not just the feed forward layers. So yeah, that's what we call as pre-train, because you have a BERT model that came out of this step, and then fine-tune because you are trying to fit that pre-trained large language model for some downstream task. So now this prompt learning is again a new learning paradigm that people have been recently talking a lot about. So again, if you look back to the fine-tuned, pre-trained or maybe just fully supervised setting, one of the things that you might have noticed is we are trying to push the model to fit the data that we have. Whether it be pre-trained, fine-tuned or fully supervised, we are trying to learn those set of weights that kind of learns to classify the data that we have. Whereas this new paradigm talks about the reverse way. And what it exactly says is, since we already have language models with us, right? Can we not use them directly to make these predictions? And moreover, can we possibly not tune them further and still make a prediction for some unseen tasks? Possibly the notion of few shot or zero shot learning. Okay, so under this, what you exactly do is, you have let's say original input sample X, you modify it using some template function and generate X bar out of it, which will have some unfilled slots that your model has to now predict. So for example, if you still consider the case of sentiment analysis, let's say, and let's say the test sentence that you have looks something like this: I really liked Squid Game. Let's take this example because people have been talking about a lot about this new series. Now we want to say whether it's positive, negative or neutral. And the condition that we are operating under is that we just have a language model in our hand. And the language model that we have is trained on abundance of data. It could be from just plain English to also incorporating all the reviews on the internet that we have. So it has kind of all the word knowledge what we can think of. So clearly in that corpus, we must have had a lot of reviews that could have been formatted in this way or maybe some other way. So clearly the language model should ideally now know a positive sentiment or negative sentiment or neutral for say. So if I transform this S into S dash, that looks something like, let's say, watched Squid Game, full stop, then a space, and then possibly a word, it, let's say. So let's say this is S dash that I transform out of this S. So now the intuition is that since model already knows a lot about such sentences and the possible number of constructs in which sentences around particular sentiment might occur. So if I give this to my language model, it should possibly fill this space with the word, let's say, liked, or possibly disliked, or maybe didn't like. All of this could be the possible things that it might fill. And once it does it, you can have a mapping created that kind of maps a particular type of words into a sentiment of, let's say, positive or negative or maybe neutral. So clearly, if you notice, we are trying to model our input sample into a format that possibly a language model might have seen during its pre-training phase. And then from that knowledge, we are trying to predict this empty space. So clearly there's no extra model that we are learning. Unlike the pre-train and fine-tune stage, where for every new task, you'll have new set of weights. So that's the power that we're talking about when we talk about prompt-based learning. So obviously you'll have a lot of difficulties as well because clearly things can't be that easy, right? So we'll see to what all problems exist when we talk about prompt-based learning. But yeah, I think now you must have gotten the idea to what we are essentially going to talk about for the next 20-25 minutes. Cool. So let's move forward. So if you see this table, this also talks about the 4 paradigms that we have been witnessing from early on to this year of 2021. So the first one was the fully supervised setting, which is again the non-neural network days. You would kind of do feature engineering by hand depending on the task that you're trying to solve. Now this could be like part of speech, all the lexical features, the sentence length, diversity, readability, and all sort of things, and then try to fit a model for that particular task. So here all these red color boxes that you see essentially signify that the task, what they're representing, has to be solved in a supervised setting. So this is nothing but classification, sequence tagging, and sentence generation. And language model is a unsupervised way of training, or to be more precise, it's a self-supervised way of training, which is represented as blue color. And clearly you can see there's no arrow going from LM to any of these tasks or any of these tasks coming into LM, because in those days we didn't used to use language model essentially to solve these tasks, right? So the second one was again fully supervised, but here we had started using the neural networks. So clearly the diagram again looks same because again there was no notion of pre-training that we had. You can think of these days as just using RNN for training a sentiment classification or text generation, so to say, or maybe just a feed-forward network with word embeddings. So all of those were again the days where we didn't use the notion of pre-training. Then from 2017 onwards, we started doing this paradigm of pre-train and then fine-tune, where you have a language model that's trained in a self-supervised fashion, and that's kind of powering all the downstream tasks. And now each of the tasks that you see is nothing but is a stack of an unsupervised thing followed by a supervised setting. Similarly for the classification, you have an unsupervised phase and then you have a supervised phase, unlike text generation, which can be done directly using the language model. And then what is of interest as of 2021 is the prompt engineering, which is you pre-train, you prompt, and then you predict. Okay, so also one more thing, if you notice this figure, all the arrows are going outwards from this language model cell, because the language model is kind of powering, or everything else is kind of built on top of the knowledge what language models already brings to the table. Whereas in this D figure, all the arrows are coming inwards, which essentially is again a sign is that all the tasks are now kind of reformulated and modeled in a way that they satisfy the language model pre-training that it has already gone through. And you possibly need not require to train another model for every task that you have. So yeah, that's about the 4 paradigm that we have in NLP. Okay. Okay, so starting off with the prompting basics. So under supervised learning, in order to train a model that has a parameter theta, given a sample X tries to learn this class Y. So it is kind of necessary for you to have that large amount of data for any particular task that you're trying to model on. Unlike the prompt-based technique, where as we saw, right, we are trying to model this sample in such a fashion so that it kind of maps the distribution on which the language model was trained. So which means you just need raw data to train your language models. And this is pretty much easy, right? Because we have so much of data already available with us and use that to predict our label, which is Y. Okay. So let's familiarize with the notations and the terminologies. So input is X, output is Y. So let's say the example is I love this movie, which is the input to the model, and the output that it has to predict in case of sentiment analysis, which is Y, will be very positive. Now again, the input could be one or multiple text. The output could again be one label or a text that you want to generate in case of, let's say, text summarization. So that's about input and output. Talking about the prompting function. So we define f prompt that takes in this input X and transforms it as per certain template in this format. So I love this movie would kind of plug in over here. Then overall, comma, it was a Z, which the language model has to predict, and then movie. So this way you're kind of transforming your input so that it becomes easy for your language model to make this prediction. So again, if you read, the function that converts the input into specific form by inserting the input X and an adding slot Z, where the answer Z may be filled later. So yeah, that's about the prompting function. Moving on to the flow, how things would work end to end. So once you pass X through a prompting function, you get X dash. So which is where you insert the value of X. I love this movie. Overall, it was a dash movie. Now, once this goes to the language model, depending on how likely and how many times does the model see such sentences, it will predict this Z word. And in this case, let's say it might say bad or good, for example. And as we know, like at any point T, you will be having this softmax distribution across the entire vocabulary. So these could be like, let's say, possible 3 words that the model might fill. Now you might be thinking, because we needed like if it's a positive sentiment or negative sentiment, but here the model is kind of giving us one word which clearly doesn't signify which sentiment we are talking about. So yeah, that's pretty true. One of the ways is to kind of maintain a dictionary of certain good words that map to, let's say, positive, and certain bad words that map to negative. And depending on prediction that your model makes, you can do a lookup and return its corresponding label. So yeah, that's one way to how you can deal with that. But the overall idea to how it goes from end to end can be clearly seen in this table. Okay. So here they again write the same thing what we have seen in the above figure. And also, for example, if you're dealing with a machine translation task, then your template might look something like this. Finnish X English Z, where X is nothing but the Finnish text that you want to translate to English text. And Z is nothing but the prediction that your model makes. So clearly with the sentiment analysis, which is the classification task, and the text generation, which is the machine translation task, we can see, right, Z can occur either in the middle somewhere or maybe in the end. So if it occurs in the middle somewhere, then this can clearly be seen as a close prompt, because you're trying to predict somewhere in the center based on the context in which that mask token is occurring. Whereas the second type of prompt, wherein the Z is in the end, such as in the case of machine translation, you can call it as a prefix prompt, because the prefix is what you give based on which you're trying to predict what the Z token should be. And as we can see, the template need not be proper English like we had in the sentiment analysis case, where we appended a language such as overall it was a and then the word movie. It could be like keyword based oriented, and that might not even make sense, for example. It totally depends on the distribution and the kind of data on which your language model is essentially trained, because you're trying to mimic the same thing while doing this inference. So for example, in the case of machine translation, you just add these keywords and nothing special in terms of adding a proper English. So yeah, that's again one thing to note down. Now talking about the answer search. Okay, so as I said, that at any step, your language model is essentially doing a softmax over the entire vocabulary, which means not necessarily the first one. You might have n number of top candidates that might fit in that particular mask token. Okay, so it might very well be possible that your model outputs more than one number of words that might fit that particular sentence. For example, in the case of sentiment analysis, we can see like excellent, good, okay, bad, horrible, all can easily be fitted in that particular sentence. And then for each of them, we have the sentiment labeling. Now the question is which one to essentially choose. So the idea is pretty simple. You choose the one that kind of maximizes the likelihood of the entire sentence. So this X dash is nothing but the transformed input representation. You fill the Z space that you have with possible Z's that you have with the model that has parameters theta. Whichever maximizes the probability of the entire sequence, you choose that one. So yeah, that's about it. Also in case of Z, if it is multiple words that you want to generate, then beam search is something that you can try out over here. Okay, they have also mentioned certain terminology. If any prompt goes through the entire process, then we call it as filled prompt, because you now have something filled in that position. If that position has now the correct answer, then we call it as answered prompt. Okay. Now talking about the next section, which is answer mapping. So till now we have the highest scoring answer Z, but we want to map it to Y, because again, if you get a word excellent that the model predicts, you should be able to conclude that it's a really positive sentiment. Or in case if you get a word horrible, let's say, that your model predicts, then you should be able to map it out and say it's a negative sentiment. So let's see what they talk about in this section. Okay, so they also mentioned that there should be a mapping that kind of matches the searched answer to the output value. Okay, so this figure is there. Okay, so in this table, they essentially discuss the type of task, input, what could be the possible templates, and what could be the answers that the model can generate. So for example, if we talk about classification, which could be, let's say, sentiment, topic, or intent. So if we see this example, what's the taxi fare in Denver? Then one of the templates could be this, where you fill in this input and then append this string followed by this empty symbol that your model has to now predict. Then these could be the possible answers that it might say. If you talk about, let's say, named entity, this is your first input, this is your second input. You can format them in this way, like Mike went to Paris, then you have a space, then Paris is a dash entity. Now clearly the answer should be location. So yeah, that's how we expect a model to kind of output the word location from its prior learning. And if we see the text generation systems, which could be, let's say, summarization or translation. So let's say if we have a pretty long input that starts with Las Vegas police, blah, blah, blah. You put that in the starting, add the keyword TLDR, and then expect the model to kind of fill these Z values based on this given prompt. So this, if you remember, was also mentioned in the GPT-2 paper, where the authors had tested the zero-shot capability of a pre-trained language model, which was GPT-2 in that case, where they just appended the keyword TLDR and saw a certain sense of summarization behavior that model has already picked up based on the input corpus on which it was trained. So yeah, that's pretty amazing, and you can kind of think of it to be one of the prior works that found this behavior accidentally. But clearly now we have a lot of literature that justifies it and is trying to improve that. Okay, moving forward. Okay, so now talking about the considerations that we need to make at every step while designing a prompt system. So the first thing is to choose a pre-trained language model. So clearly that's the center part of the entire thing to what we have seen till now. So a language model that has been trained on large, diverse variety of text and still has a pretty low perplexity is what we want to target for. Then the second is prompt engineering. So clearly the entire task is to model an input sample in a way that it might have occurred in a language model space is what we are trying to do. So clearly designing these prompts is a very crucial task, and the performance of your downstream tasks clearly depends on this. Then the third one is answer engineering. So you need to design possible number of Z's that if a model spits out during the prediction time is what you want to map to the Y label. So clearly having a set of those Z's and a mapping function that does a mapping from Z to Y is what you would want. Then the fourth is basically expanding on the paradigm. So whatever we have seen till now is one of the simplest ways to how you can do this prompt engineering. So there has been a lot of advanced work that has been done in this domain. And as we proceed forward, we will see what those works are. The final one is prompt-based training strategies. So till now, whatever I have said was that we have a pre-trained language model. You transform your input sample in a certain way and then pass it for inference with that pre-trained language model. But clearly you can go about having a separate stage of fine-tuning that's just based on the prompt. Or you can even append a prompt to the input samples while pre-training your language model. So all of these possibilities still exist. And in this section, we'll see to all of the work that has been done in this domain. Cool. So from here on, we'll expand to each of these points in detail and see the relevant research that has been done. Okay. Okay, now we start off with the third section of pre-trained language models. So I think this is a good time to stop and leave rest of the paper for the follow-up videos that I make, because I'm pretty sure if this video now after editing crosses, let's say 20 minutes, my iPad is going to lag a lot now. So yeah, I also need to take care about the logistics, I guess. So yeah, cool. Let's see to what we'll be covering in the next one. So in this video, we have covered first and second section. So for the second one, pre-trained language model and prompt engineering, basically these two sections again. And eventually again in the follow-up videos, we can cover rest of the section and proceed with that. Cool. So if you appreciate my efforts, make sure to hit that like and subscribe to the channel. Also share it across with your friends to whosoever is interested in such content. I'll meet you in the next one soon. Bye bye and take care.